chemistry. Okay. That's all. So are you seeing me? I just check if you're seeing me. Thank you. Hello, everyone.
Yeah, I'm checking.
Okay.
Yes, we are live now. People are seeing.
Okay. Thank you very much. Can you hear my voice? All right. Okay. Hello, everyone. I want you to say hi if you're hearing my voice. Let me know that you're here, that you're hearing my voice. Can you hear me? Today we want to talk about, I promise you that we're going to talk about organic chemistry. And we're going to start dealing with the first section, the first 3 topics we treated. Normally the time will not permit us to do all the discuss 3 sections together, but I will try as much as possible to see how far I can go to make sure that this time is worth it for you. I want to share this slide. I want to briefly talk about can you see my screen? I'm sharing my screen now. Yeah, I want us to talk briefly about organic chemistry. I said at the end of today, you will not be afraid of organic chemistry again. Can you see my slide? I want somebody to talk to me. If you can hear me, my voice. Actually, oh God, all right. Well, we are going to start the first topic we treated, which is factor that influence reaction mechanism. So, I want to explain to you covalent bonding. I want to go through the slides so that we can ask our questions. Covalent bonding. In covalent bonding, the electrons are not static. It means that these electrons are mobile. Then when you are having two similar atoms coming together to form bonds, these atoms, because they are similar, the electrons that are mobile will be shared equally. That's why they call it symmetrically disposed, because they are equally shared because they are similar. In that kind of bond, it is called non-polar covalent bond. Why? Because the atoms involved are the same. That's the kind of bonding that exists in something like hydrogen molecule, chlorine molecule, oxygen molecule, those ones that are similar. In the same vein, there are some atoms that are not similar and they come together to form a bond. Because they are not similar, these mobile electrons that are not static are not going to be shared equally again. How? Because they are not similar. So the higher electronegative atom is going to get higher share of this electron. Example is what we see in hydrogen and chlorine. So because chlorine is highly electronegative, more than hydrogen, so the pool of electron will go to chlorine, making it asymmetrical or not symmetrically shared or disposed. So that's what we call, because of this electronegativity of chlorine, the bond is termed to be covalent bonding. This is the example of what we are talking about. You can see hydrogen, because they are, and chlorine, because the atoms are similar, the place you're going to see division means that they're being shared equally. The electrons are being shared equally. But in case of hydrogen and chlorine, the electrons are not shared equally. You can see that electron moving towards chlorine more than hydrogen, making this bond to be polar covalent bond. Now, the bond that is not symmetrical, which is polar covalent bond, because of partial dispersion of these charges, we call it partial ionic covalent bond. But any covalent bond that does not involve partial dispersion of ionic charges, we call it normal covalent bond. But remember, these are what makes this bond to be polar because of the partial dispersion of the charges. Now, we talk about inductive effect. I told you in class that inductive effect is a situation where a compound that is not polar at all becomes polar because the neighbor is polar. So because of the polarity of the neighbor, this compound becomes polar. That's what we call inductive effect. Simply put, carbon C1C2 from this structure is not polar because the carbons are the same. Remember, like we said, when the atoms that come together are the same, they become non-polar. So they are non-polar because carbon and carbon are the same. So if you want to share the electron cloud, you're going to share it equally. But because chlorine has been attached to carbon chlorine, making carbon C1 chlorine very polar. Because of C1 chlorine is polar, CC that is non-polar will become polar. That is effect called inductive effect. And that's why I said that when somebody that is not feeling sleepy, say beside somebody that is feeling sleepy, that's a sort of inductive effect, inducing sleep in someone that is not feeling sleepy. That's inductive effect. Now, this inductive effect is a permanent effect because as long as that compound is polar, the compound is polar. That's why we call it permanent inductive effect and occur through a sigma bond. But when you come to next thing, you ask yourself, this inductive effect are true because the substituents that attach to this compound will determine whether it's going to be positive inductive or negative inductive effect. What's the effect of those two? We'll see at the end. Now, negative inductive effect means that electron withdrawing. When you're taking, it is negative because you're, like I normally talk, you are basic. It's like you're on debt by collecting. So that's why it is negative inductive effect. Now, the compound that does that is mainly halogens. Then other ones like NO2, cyanide, sulfonic, the aldehyde alketone, and esters. These are compounds that can withdraw electron or attract electron. Because they are collecting, they are on negative inductive effect. Remember, inductive effect is something that is not polar becomes polar because the neighbor is polar. Simple put. Then we have another one that is positive inductive effect. This is where electron is donating. So when somebody is giving you, the person is adding to your life. When something is taken from you, the person is removing from your life. That is negative. So but when electron is being added to a compound, the presence of that electron gives positive inductive effect. Now, what's the sense of this? Now, if you look at this compound, carbon has so many electron donating groups on it. Now, the more the electron donated group, the more the inductive effect. But my question is that what is the essence of this inductive? What does it tell us? When there's electron donating effect, electron donating group on this carbon is going to help carbon to be acidic. So the more the electron donating potential, the higher their acidity. Now, another effect we're going to look at is electromeric. Inductive occurs by a single bond. Electromeric occurs by a double bond. Remember, this thing must be carbon-carbon bonding. There must be bonding. Now, in this case, carbon is bonding with another electronegative atom, which is oxygen. The presence of this reagent will cause this bond, this pi bond. Remember, pi bond is a weak bond. So the presence of this reagent will cause the pi bond to break towards electronegative atom. Remember, there is always a pull of electron towards electronegative atom. Oxygen is electronegative. So the pull of electron is going towards oxygen, away from carbon. Now, this effect says there's a complete transfer of these electrons that are being shared by carbon to oxygen. With this bond, remember every bond is made up of 2 electrons. So this bond is completely transferred to oxygen because oxygen is highly electronegative. And because of this reagent that is there. So when this reagent is taken away, the reaction reverses back. That's why it's a reversible reaction. So when there's a complete transfer of electron to one of the atoms that is bonded by either double bond or triple bond, we say that this is called electromeric effect. Now, why is it a temporary effect? Because what initiated it is that reagent. So when the reagent goes out, the effect goes back. So it's not a permanent effect. And unlike inductive, this must occur through double bond or triple bond. There must be multiple bonds. Might be double, might be triple. Now, what is resonance? Resonance is there is a movement of electron density from when it is where there is high electron to where there is low electron. So simultaneous decrease of electron density from one position to corresponding increase. Look at the structure we have. Now, the double bond is electron rich, single bond is electron deficient. So the movement of this double bond is going to make that double bond that is electron rich to be electron deficient, having positive sign in the next alternate structure. While the one that is deficient by having plus is going to be rich by having double bond. So that's what we talk about resonance. So there must be simultaneous increase. As one is increasing, the other one is decreasing. That's the same thing with mesomeric, because both of them are conjugative effects. Conjugative effect means it occurs in the conjugative system, but there's a little similarity between the two of them. People are going to see. Now, in terms of resonance, not all compounds can undergo resonance. There are compounds that cannot undergo resonance. Now, for a compound to undergo resonance, they must be conjugated. A compound that is conjugated is when double bond alternates single bond. That's conjugated. But there are some compounds that cannot undergo resonance. The ones that are not conjugated, which is isolated. When a compound is isolated, it means that double bond is not alternating single bond. So there might be double bond, then two single bond, they find another double bond, or double bond and single bond all through. So when there is no conjugation, there is no resonance. Now remember, for resonance to occur, there must be pi bond alternating sigma bond. And in resonance, the more the canonical structures is the resonance hybrid of all, is the resonance structures from a particular compound. So the more the resonance structures, the more stable a compound. So because canonical structures have higher energy than the hybrid. Hybrid is, example of hybrid, let me use this to explain it. When you talk about hybrid, hybrid is a summary of resonance. The canonical structure are the resonance structures of a compound. A compound cannot have just one resonance structure. So the more resonance structure a compound have, the more stable. And this resonance structure is also called canonical structures. So when you talk about, but in terms of hybrid is where all the resonance are summarized. You can see that there are dispersion of charges, meaning that this has low energy because everything is stable. Why the canonical structures have higher energy than the resonance hybrid. So when we are talking about resonance, we normally use arrows to show resonance. The arrow must be equal arrow going up and down, because resonance is like a reversible reaction, so there must be double arrow. And in resonance, you must know that the atoms are not moving. What moves is the bond, that's electrons. So the atoms are always only the electrons that are delocalized. Electrons are the one moving in resonance. The atoms are not moving at all. Now these are the signs of resonance. When we are using double-headed arrow, it means that the two bonding electrons are shifted. Just like the second one, it means that now that's what we do to have radicals. When there are equal sharing of these electrons, by the arrow. The arrow is meaning that we are sharing equal. The first one, the arrow is heading towards electronegative halogen. But the second one, the arrow is being shared equally. So whenever we are sharing things equally, we are going to form radical, as we're going to see in the subsequent slide. But when we are sharing one, now remember, where the arrow is heading to is going to deposit negative. Where the arrow is moving away from is going to be deficient. Just like giving money, you're going to base, that is negative. The person you're collecting from is you're indebted to that person. So that person is positive because the person have money. But to you is negative. Despite that you have the money in your hand, but it is negative because it is borrowed. So wherever the arrow is going, it's going to deposit negative. Where the arrow is coming from is going to deposit positive. Now this is an example of a conjugated system and isolated system. Now when isolated system means that either double bond, then you have another 2 single bond or 3 single bond before another double bond. Then when you talk about cumulative is how when you're having double bonds consecutively, like 2 double bonds before any other thing. But normally it's not always feasible in organic system. And that's cumulative. Example of resonance is buta-1 thread diene. Now if you look at it, you realize that the double bond is the one moving. Double bond is going to move to single bond. Then the single bond, because 2 double bonds cannot stay, when they stay, they become cumulative. So as they are coming, this other double bond needs to move because the valency of carbon, which is 4, must be maintained. So in these 4 structures of butadiene, you realize that 1 and 2, 1 gives birth to 2. Then the 3 is a product of the last one. Why? When the arrow is moving away from carbon 4, it's going to deposit positive charge on carbon 4. When the arrow is moving away from carbon 2 is going to have positive. But remember, because there is positive on carbon 2 and negative on carbon 3, that's why we're going to form another double bond. I said in the class that where positive and negative are joining together, a bond is being formed. Because a bond is either made up of 2 radicals or cation and carbanion. So that's why in this 3D, this butadiene is very stable because the canonical structure or the resonance structure are 3. That is why they are very stable. Then the question is that what are the structures that shows conjugation? Now, how do we know a compound that can show resonance? Number 1 is that a structure that have double bond or triple bond conjugated to p orbital. A p orbital is any compound that belongs to that has at least 8 p orbital obeys octet rule. It means that the electron on the atomos shell, just like chlorine, if you look at chlorine, the atomos shell of chlorine is 7. So chlorine is going to use 1 for bonding, so it's remaining 6. So because of that, chlorine is regarded as p orbital. Atom that has p orbital. Hydrogen does not have p orbital because hydrogen obeys duplet, while chlorine obeys octet rule. Now, when p orbital contains 1 electron, a resonance can occur. This is the example of this is allylic carbanion. When the p orbital is empty again, that's when we are talking about allylic carbocation. So number 1 is there must be allylic vinyl chloride, a vinyl chloride, double bond, alternating single bond, and p orbital. This one is now double bond and carbanion. This is negative. The other one is double bond and carbcation. So these are compounds that must undergo resonance. So it's not just only benzene that can undergo resonance. In a class test, then you might be asked which of the following compounds cannot undergo resonance. Number 1 is that double bond alternating single bond. Now in that single bond, are we having p orbital? Now if that p orbital contains 2 electrons, it can undergo. Now double bond alternating single bond, that last single bond, the atom there, does it have carbanion or carbcation? They can undergo resonance. So understand that it's not only benzene that undergoes resonance. Now another type of resonance is called hyperconjugation. Listen, this hyperconjugation is also called no bond resonance. Why are they called no bond resonance? Because in this hyperconjugation, just like normal resonance is movement of bond. But in hyperconjugation, when bond is being moved, the atom is still there without bond, but there is resonance involved. Now, it occurs in saturated system. Sigma bond. It involves sigma bond electron as well as pi electron. Sigma bond as well as pi electron. But normally, when this hyperconjugation is occurring, sigma bond is the one that is moving. Pi electron is not moving. Now, number one is compound must be sp2 hybridized. Why is it sp2? Because of double bond. Whenever I see double bond, is sp2. Whenever I see single bond, it is sp3. Whenever I see triple bond, it is sp. Remember, we said in terms of S character, single bond has higher S character. Why? Single bond has the least S character because P is 3, while S is 1. While triple bond has the highest S character because they are equal. So the more the S character, the more the acidity, which means triple bond should be more acidic than single bond. Then why single bond should be more basic. Another thing you should know that whenever a compound is highly acidic, it is least basic. When a compound is least basic, it's highly acidic. They are always interchanged. So understand it. So whenever the question is which of the following is highly acidic, look at the one. No, but that's anyone that is least basic is highly acidic. Please prepare your questions because I just want to rush through this. Now look at no bond resonance. I know we've talked about this in the class. Why is it no bond resonance? If you look at this resonance, you realize that the hydrogen still maintains its position, but there's no bond. There's no bond connecting carbon and hydrogen. That's why they are called no bond resonance. So hyperconjugation is also known as no bond resonance. So it's a type of resonance that does not have any bond involved. If you look at this all the examples of hyperconjugation, realize that this one is carbanion. Why is it carbanion? If you look at the bond of hydrogen and carbon. Now, for a compound to undergo hyperconjugation, the more the hydrogen on alpha carbon, listen, alpha carbon is a carbon next to that carbon that bears what? The functional group. This functional group here we're talking about now is what? The double bond. Now, the more the hydrogen, the more the canonical structures. Now, if you look at this structure 1, we only have one hydrogen. So it means that we can only have only 2 canonical structures. That's resonance structure. But if this hydrogen is 2, we are going to have more than this. We are going to have 3. So if the hydrogen is 3, we are going to have 4. So the more the hydrogen, the higher the canonical structure. What are the rules that governs resonance? For a compound to have resonance, there must be conjugation. The atoms, the electrons must be delocalized. Atoms are not moving, don't forget. Hydrogen is an atom. Hydrogen cannot move. It's only electrons that are moving. And they must lie on the plane so they can be maximum overlap. So one cannot be up. That's why whenever there is something like steric effect, there might not be resonance because of the effect of that steric. So the compound must lie in plane so they can easily overlap. Like you're talking about butadiene is a perfect example when you're talking about canonical structures because of the movement of the bonds. If you look at that, you realize that compound 1, 2, 3, and 4. Compound 4 is not a canonical structure. Why? Canonical structure must have either positive or negative charge. But if you look at the compound 4, we are having radicals. Because of that radicals, compound 4 cannot be a canonical structure because it has lone pair, which is a radical. Why 1, 2, 3 have positive charge or negative charge, making them canonical structure. In canonical structure, there's always dispersion of charges. Dispersion is sharing. Charges are being shared. Charges we are talking about is positive end and negative end. They are being shared in canonical structures. So whenever you're looking, they are asking which of the following is a canonical structure. Follow the movement of the arrow and look at the one that is going to give you carbocation and carbanion. They are canonical structures. Anyone that gives you radical is not a canonical structure. Very, very important. Now this is hybrid. Why is hybrid having lower energy? Because in hybrid, all the charges are being dispersed equally. There's no tension. If you look at the canonical structure, either one end is having positive and the other end is having nothing. So it means that the energy is high because the charges are one-sided. But in hybrid, the energies are the same because everything is shared equally. So there is no tension. So that's why canonical structure have higher energy than hybrid. And remember, the more the canonical structure, the more stable the compound. Then hybrid is more stable than the canonical structure. Why? Because of low energy. Everything is shared, so there is no tension. That's why they are more stable than the canonical structures. In all the canonical structure, they cannot contribute equally. Why? Because just like in a family, if a family only one person have money, there is tension in that family. But if there are people that have everybody is okay in that family. In that being okay, some will have more money than others. So if there is any event that people are doing, people are going to contribute by virtue of how much they have. So that's why canonical structures cannot contribute equally to the hybrid because they differ. You must understand that their contribution is not the same. They contribute according to their capacity. And they also depend on, like I said, the more the canonical structure, the more the stability, and the larger their contribution to the hybrid. When a canonical structure is stable, the more stable a canonical structure, the more stable the hybrid, because they're the one that will contribute to the stability of the hybrid. Now, how do we identify a stable canonical structure? For you to know a stable canonical structure, number one, you talk about the covalent bond. The more the covalent bond, the more the more the stability. If you look at these structures 1 and 2, structure 1 has how many covalent bonds? 1, 2, 3, 4, 5. While structure 2 has 4 covalent bonds. Remember, covalent bond is that bond that links 2 atoms together. Now, double bond is 2 covalent bonds. Single bond is 1 covalent bond. So that's why 1 is more stable than 2 because 1 has more covalent bond. Secondly, the more the charge that separates, the lesser the stability. Because 1 has no charge separation, 1 is more stable. So when there is increase in charges, there are decrease in stability. Because charges are like tension. When there is tension, whether positive or negative tension, there is no stability. That's why even when you are excited, you're not stable. Very, very important. So the more the stability, the lesser the charge dispersion. From this slide, you can look at, in terms of stability, another thing you need to talk about is that any compound that obeys octet rule and duplex rule are stable. That if a compound did not obey, now look at 1, 2, 3. The third one does not obey. Why? Chlorine is supposed to be, if you look at the bond here, chlorine is having 10 electrons, which is not supposed to be. Because of that, chlorine is not obeying the octet rule, making it not to be stable here. So the only one that obeys octet rule are structure 1 and 2. So now whenever you're looking at the stability of compound, you have to also look at the one that is obeying this octet rule. We have to look at the stability of the dispersed charges. All these things are very important. So, types of resonance, we have positive resonance, we have negative resonance. Electron donating is going to cause positive resonance. Electron withdrawing is going to cause negative resonance. What are the sense of this resonance? Resonance help us to determine the stability of a reaction intermediate. They help us to know whether they are stable or they are not stable. Now, how do we generate our intermediates? Remember, we're talking about intermediates. Either homolytic, you're forming radical, electrolytic, you're forming what? You're forming your carbocation or carbanion. Now, in terms of radicals, this part is very important. How do we predict the stability of this compound? Now, remember, benzyl free radicals and allyl radicals are very stable. Tertiary are stable, secondary are stable, but methyl or primary are less stable. So if the same thing is what happened in carbocation, but in free radical, the same thing happened in carbocation, but in carbanion, the reverse is the case. Now, in carbocation and free radical, the tertiary is more stable, but in carbanion, the most stable one is the methyl or primary. Very, very important. Now, I think I want us to ask questions now, if you're online, because the essence now, which of these is the most stable species? If you look at it, you realize that this is radical, this is carbocation, this is carbanion. Remember, like we said, in terms of stability, carbocation and carbanion, the most stable ones are tertiary. Carbocation and radical, the most stable ones are tertiary. But in terms of stability, the most stable carbanion is methyl or primary. So the most stable species here is what? The carbanion, the negative charge. So when there are methyl, when there are electron donating group, negative cannot be stable. Negative is stable when there is electron withdrawing, because they are negative already. So when you are dropping more electron to them, they are destabilized. I gave an example in the class that if you have money and people are giving you money, don't appreciate it. But there's a time you don't have any money, somebody is giving you 100 naira. That day you're going to appreciate the person because you're electron deficient and the person is giving you electron. It's going to make you more stable. The next question. These all the canonical structures we're talking about: allyl radical, allylic carbocation, and allylic carbanion. We can also have them in benzylic form. These ones are very stable. So when I have my benzyl, whether it's radical or carbanion or carbocation, they are very stable. Very, very important. Steric hindrance, like I said, is the effect of bulky group. They will make a compound reaction to be unstable. When you have so much load in your car, the motor will not move. So this is steric hindrance. This is another question. Among these questions, which of them is the most stable carbonium ion? Which of them is most stable? Remember, like we said in the last slide, the most stable is this benzyl carbocation. Benzyl carbocation is most stable. Second one, which of them is more stable? Is it ethyl, carbocation, or propyl? The more the methyl, the more stability. So propyl is more stable than ethyl. Then looking at this, like we said, tertiary is more stable than methyl. So, but if it's in terms of carbanion, it means that methyl is more stable. Please don't forget this particular point. It's very important. I want us to ask questions. Now, see, which of them is more resonance stabilized? Resonance stabilized is different from the other one we're talking about. In terms of resonance stabilized, you're looking at conjugation. The number one, which one is the first one? The most resonance stabilized is I, not the second one, the first one. Then the second one, I, the more resonance stabilized is the second one. because of the double bond. The third one, the more resonance stabilized. Look at this, is electron donating. This is electron withdrawing. Electron donating is going to destabilize because this one is negative spatial already. So because of this, the electron withdrawing NO2 will make the more resonance stabilized. So that's the end of the slide. So I think we can ask question now. Can we ask our question? Can you ask question? If you can see me, ask your question. Hello? Can I hear someone? Question time. What's happening? What's happening? Ask questions, so my students. Where's the message? Oh, music. Oh, I'm sorry. I'm sorry. I'm sorry for the background music. Oh. Where did I put that music? I don't know where I put that music. How do I do them to talk? Now let me answer your question one after the other. I'm sorry. Let me answer your questions. Oh, this sound. Why did I even add that sound instead? Let me try to remove this sound. Oh, sorry for this sound. Where did I add the sound for? I think this sound, I don't know why I added it. I'm finding it difficult to remove it now. Let me answer your questions. If you can hear me now, let me answer your question. After this, I think the next video will be better than this. Because I am really sorry for the way I planned it. It didn't come out that way. But I know. Okay. Let me. Oh. to remove this sign. I want to remove this sign. I want to remove this sign. So you can hear me very well. I want to remove this sign. Sorry, I have to remove this sound though. I'm not very conversant with this live streaming. This is my first experience. So that's another issue. Okay, like this. I have to answer your questions. So removing this audio now is distracting me. Oh God, that me. So let's just be talking that way because I don't know how to remove this. Okay, what is this? Stability of carbocation and carbanion. Let me answer your questions. Maybe no, I don't know how to remove this term that I added. Now let's go. Please, I think the next one will be better than this. Just prepare your questions. I will try and repeat this thing tomorrow so that I will take all the errors I made today, then I'll correct them. So we're going to have a free flow tomorrow. Okay, question. I'm sorry. I don't know how to remove it. They had the S character, they have acidity. Is that correct? Yes. Yes, that's why triple bond is more stable, is more acidic than double bond. Double bond is more acidic than single bond. So sp3 is highly basic and less acidic. Is sp higher acid? Yes. sp has a higher acid, is highly acidic, while sp3 is the least acidic. And remember, least acidic, when a compound is the least acidic, is highly basic. So that's why sp3 is highly basic, while sp is highly acidic. Yes, I'm responding to the questions. Now, the higher the electron donating agent, the more the acidity in the compound, not all compounds. Now, when a compound is electron deficient, electron donating can stabilize. When a compound is negative already, electron donating is going to increase basicity, right? So electron donating can increase acidity and depending on the compound. A compound that has positive species, donating will stabilize. But electron withdrawing group. If I have a compound, example, I think I would have uploaded the slide, the second slide, where we're talking about acidity and basicity of a compound. Now, if I have a compound that donates electron, depending on the species that the compound is, it can be acidic or basic. But remember, in a benzene ring, electron donating is going to be outer para directing and activate the ring. But if you're looking at straight chain, aliphatic compound, and a compound is deficient already, donating is going to stabilize it. It's going to be acidic. But when a compound is highly electronegative and you're giving it electron, it's going to be highly basic. In that case, for you to increase acidity of that compound, you have to withdraw electron. So nucleophilic species, that's negative, you withdraw to make it acidic. Electrophilic, that is positive, you donate to make it acidic. If your question is answered, time is answered. If not, we're going to come tomorrow to ask more questions. And that tomorrow, we're going to deal with others. I've talked about today the first topic we treated. Tomorrow I'm going to rush through the second and third. The challenge we had today was because of this is my first time of live streaming. This is my first live streaming, so that's why it's very challenging. The next one tomorrow is going to be perfect. So that's why I did today, so that we can have time tomorrow before your class test. I'm sorry, the next video I'm not going to put any background music. I know. I didn't realize it now. Now I've edited everything. Getting back now, I hope I can see it again. So I don't want to do anything that will affect this question. Let me just answer the questions. Difference between canonical structure and resonance hybrid. Canonical structures are resonance structures. Resonance hybrid is like combination of all the canonical structures. Resonance hybrid just like summary of all the canonical structures. But remember, canonical structures are simply what? Resonance structures. So in hybrid, you're going to disperse all. That's why you see in hybrid, they use dotted lines, put positive, meaning that positive goes around. But in canonical structure, you're going to tell us where the positive is here or is in that other place. So you're going to tell us the exact place where the positives or negative species are. But in hybrid, you're going to share everything together by using dotted line and the positive center. Steric effect. Steric effect is effects that steric effects occurs because of the presence of bulky group. If I have a bulky group in a compound, that compound cannot react very well because of the steric effect. Example, if I have a compound that has all the like carbon, if a carbon is connected to 4 bonds and all the 3 bonds are something like phenyl group, because of that phenyl group, the reaction will be very bulky. There will be no space for any reaction to occur. Just like if you're traveling and you have load, another person is traveling without load, you can see the movement will be different. The one that does not have load will move faster. The one that have load is going to drag. That's what happens when more people are inside the bus, like this former bus that is called Molue. If you're there, the bus drags because of the crowd, because of the load. But the bus that is very free, like this new blue bus, blue BRT, people fly. The movement is faster because the load is being dispersed. It's not crowding. So that's steric effect. Which is stronger acid, fluorine or chlorine? The answer is the one that has chlorine. Why? If you look at the one that has fluorine, we have CH2 and CH2 before carboxylic acid. But the one that have chlorine, number one, we have only one methylene before carboxylic. So the effect of an inductive effect of the chlorine and that of carboxyl is on this methylene, so making it very polar and highly acidic. So the answer is chlorine that has one methylene. The problem is that other of fluorine has 3 that's propyl before the carboxylic acid. So that is why it is least acidic. I've explained the canonical structure. The canonical structures are resonance structures. The same thing like resonance. So if you're talking about canonical structure, you're talking about resonance structures. So resonance structures is movement of, remember I said in resonance, the bonds are moving, but the atoms are not moving. So when bonds are moving, where the bonds are moving to, they are depositing negative. Where they are moving away from, they are leaving positive sign. So now when you see a compound, look at how the compound can move. Let me use this, let me see if I can use this slide to explain resonance again. I want to explain resonance again. Somebody said I should explain resonance. Let me go to that resonance slide. Now, for a compound to undergo resonance, I want us to use butadiene. The butadiene is very, very versatile in explaining resonance. Now look at this butadiene. If you look at butadiene, you see that a bond, you can see the double bond is going to move to single bond. The single bond is going to also come and deposit the negative charge on the methylene carbon. So the two compounds, the two structures are resonance structures of this butadiene. So now if I want to move back again, I can also move back. If I move back, I'm going to have another resonance structure. That it means that my negative center is going to be on my left side, while the positive center will be on my right side. So I'm going to have another canonical structure on that. So at the end, I'm going to have 3 canonical structures for butadiene. So canonical structures are resonance structures. I'm sorry about the background music. I don't know what to do about it. I'll correct it tomorrow. Yeah, I'm going to also do it that you can talk. By tomorrow, I'll see if it's possible for you to talk. So I want us to interact. Which is more stable between benzyl carbanion and allyl carbanion? Benzyl is more stable than allyl. The benzyl is more stable because of resonance effects of that benzene ring. But at times, look at the way they are graded. They are virtually almost of the same stability. But in time, if you want to compare them, benzyl will come for before allyl. The reason for answer of benzyl questions for both 1 and 2. Benzyl question for both 1 and 2. Let's go to that place. Benzyl question for that 1 and 2. Now, I said before I answer that question, I showed you this slide. In this slide, benzyl, whenever there is anion or carbocation. Now, whether benzyl radical, benzyl carbocation, benzyl carbanion, they're all very stable. But if you want to compare, we are comparing between primary, secondary, tertiary, and methyl. Remember, methyl is not primary. Now, in carbocation and radical, the tertiary are most stable, while the methyl are the least stable. But in carbanion, that one that has negative charge, the methyl is most stable, while the carbocation, that tertiary, is the least stable. So when you come to negative, reverse is the case. There's radical and carbocation is the same thing. So they follow the same trend. So go back to the slide to understand it. I'm going to upload this slide for you to see. So it can be easy for you to go back to. I'm going to upload the slide. I'm not just going to upload the slide. I'm going to take my time to talk to the slide so that you can so that even when this broadcast is over, you can go back to the slide and go through it yourself. Not just for the class test you're having this week, but for also the exam. The essence of this, I want everybody to come back and send to me a message that I got A in 2 and 3, because that's the essence of all this we are doing. Okay. The path of stability of carbocation and carbanion, I just explained that now. I don't understand the reason for resonance stability in the first question. Okay, let's go to the resonance stability. Form of resonance stability. Okay. Resonance stability. Now, in the first question, if you look at the question very well, I said the one that is more resonance stabilized is I, not II. Number one is that, see, remember the carbon that is next to the aromatic ring has a positive charge. So there is this positive charge can move around the ring. Remember, if you're talking about, when you're talking about, let me share this slide. Let me go back to show you this, what I want. If you come here, you realize that for there to be movement, this carbocation needs to move. Now, there's supposed to be a movement to neutralize the positive center on this carbon. But if there is any methylene in between them, that charge cannot be neutralized. Remember, if there is negative, you're going to move from negative into the ring. If there is positive, you're going to move from the ring to disperse the positive center. Meaning that because there is an intermediate methylene, because there is this methylene before the charges, this ring cannot have effect on this charge. But this particular first one, the double bond, which is electron rich, can actually come and neutralize this positive center, but it cannot have effect on this because of the interference of the methylene before the carbocation. That is why. Can you send the slide? You know what? I'm going to make video. I'm going to talk to the slides for you to understand. The essence of this normally is for questions. And you're going to understand with the slide. The slide will be available for you. So not just the slide, tutorial of the slide. I'm going to talk to the slide, explain everything, take my time to explain everything on the slide. And you're going to have it tomorrow. Inductive effects. Inductive effects. Inductive effect means that because you don't have money, your friend have money. Following your friend that have money, the money is going to flow to you. So inductive effect is an effect where a non-polar bond become polar because the neighbor is polar. So because of the polarity of the neighboring bond, this bond that is non-polar becomes polar. Remember, we are talking about non-polar bond is when two similar atoms join together. So carbon-carbon are non-polar, while carbon-chlorine are polar. Why? Because of electronegativity of chlorine, electron is moved to chlorine. So in terms of sharing of this electron that is not static, it's going to move towards chlorine, making it polar. So because of that, the carbon-chlorine is polar. The bond between carbon and chlorine is polar. While bond between carbon and carbon is not polar. But because they are connected together, carbon-carbon become polar because of the polarity of carbon-chlorine. The sound, I don't know how I picked it, so I'm going to remove it in the next video. Can we Zoom tomorrow? Yes, we can Zoom tomorrow. That tomorrow will be perfect. Let me know your time. What time do you want us to Zoom tomorrow? Tomorrow will be a perfect scenario. Let me know when your lectures are ending, so maybe we can start by 5 so we can have enough time to do this. Because tomorrow we are going to take time to do all the whatever you need. We've not talked about the aromatic compound. We're not talking about the factor that affects basicity and acidity. We're going to talk about everything tomorrow, so that I'll make it a section that you can ask all your questions, and some of the challenges we have today, we're not going to have it. Okay, thank you. I think I've answered all your questions. I've not finished. Yeah, okay, yes. Okay. Zoom. Okay, maybe we're going to use Zoom tomorrow. Maybe I'm going to do Zoom. Let's see how tomorrow will be. We can do Zoom so we can ask questions. I should go deep into inductive effects. Wow. Okay, tomorrow we'll do 5 p.m. Inductive effects. Hi, how I wish you can talk. Okay, Emmanuel, tomorrow I think I might do some Zoom tomorrow so that we can talk. Let's see how tomorrow will be on Zoom. Okay, so we can talk. I want to hear your voices. We'll be leaving Ijaraba. So what time is good for you? Tomorrow? Okay, 5:30 is still okay tomorrow. You want 5:30 tomorrow? I want to know your best time tomorrow. Let me know your best time tomorrow. Now, that's something I want us to know very well. Number one, like in summary of today's class, if you're asked what is no bond resonance, you know that is hyperconjugation is no bond resonance. No, I can't do 6 p.m. It will be late. You can see I'm still in school. This is 6 p.m. I'm still at 6, almost 7. I'm still around. So let's see what is. If I'll know if classes are ending, you can't be having class at 5 p.m. What class is that you're having till 5 p.m.? So we are going to vote in the general group your best time. So the higher bidder is going to win the time for tomorrow. So another thing I want you to understand is about the species, how to know stable species. We can talk about hyperconjugation. We can talk about resonance. These are things that will help us to know stability of a compound. If you want to talk about acidity of a compound, you can also use inductive effect to explain acidity. We're going to talk about those tomorrow. So what else are we supposed to know about today? We're also supposed to know today that if you're talking about mesomeric effect, what it means. If you're talking about inductive effect, what it means. So just understand them. There's going to be a replay on this, although this is not the best version the way I wanted it to be. But nevertheless, you can learn one or two things from this. Tomorrow, we're going to have a better live streaming. I will see if it's something you can talk on. And if it's not something we can talk on, we can look for another better version. But I assure you tomorrow will be better than today, because some of the errors of today will be corrected tomorrow. Please, let's make it earlier tomorrow. Let's make it earlier tomorrow. The earlier the better, so that I don't want you to be tensed up. I want at the end of the tomorrow's time online, even if you did not revise anything, you go and write your classwork, class test, and you come out smiling. I just don't want you to have, if it's over 10, I don't want you to have 7 over 10. I want you to have 10 over 10. So I want you to understand everything. So now when you get home, the slide you have already, I'm going to upload a slide before I go tonight. This particular slide, I'm going to talk to the slide and upload it, so you can listen to it again and again. And if there's anything you don't understand, you get back to me tomorrow and ask your question. Then we're okay. By tomorrow, I'm going to do the remaining 2 topics. I'm going to rush through them and make sure that everything is touched, so that you understand that. You have to understand what is Hooke's rule, how Hooke's rule is applied in determining aromaticity of a compound. So you have to understand all this. I don't want you to cram chemistry. I don't want you to be afraid of chemistry. Though this chemistry seems to be bulky, but the way we are doing it, you are going to understand that some of the things you've been seeing in past questions, you're going to have a hands-on on them. And tomorrow, I want you to ask some of those questions you saw on the past questions that you cannot deal with. Please, so that we can sort everything out. The test holds on Thursday. Yes, it's going to be online, but I'm going to tell you the modality of the test, whether it's going to be in the comfort of your zone or everybody is coming to VLI. I will get back to you on that information. But please make sure you're not afraid. Just make sure this is online. It's going to be CBT. And remember, as I normally tell you, whenever you're doing your CBT, you must make sure you read in between the lines. Electron donating group, the increased electron density of a compound, just like when you have money, somebody is giving you money, it's going to increase your money. The electron withdrawing group is going to take and reduce the electron density. Now, when electron density is reduced, it's going to increase acidity. Let's bring it life. If you have so much money, you are happy, you are stable. But if you don't have money, acid hurts. So when there is electron withdrawing, anybody taking something from you makes you sad, right? So that withdrawing is acidic because it's taking something from you. So whenever you see a compound that's talking about acidity, is it acidic? Look at the substituent. Is it electron withdrawing, electron donating? Now, how do I know electron donating? Electron donating must have, number one thing, lone pair of electron. So that lone pair is going to donate. So whenever a compound has a lone pair, just like any compound that has oxygen, any compound that has nitrogen, they are always donating. So this compound that is donating is going to increase the presence of electron in that compound. And when there is increase, there is basicity. So when electron is taken away from this compound that have, it's going to make it acidic. So the more the electron withdrawing, the higher the acidity. The more the electron donating, the more the basicity. So, if there's no other question, I think we've tried for today. Let me do the other ones and upload this slide for you. So, see you tomorrow. I will tell you the time on the general group when we're going to meet tomorrow. But please, tomorrow will be better than today. Today, I was disorganized because of where I started. So many things were not in order. But tomorrow is going to be perfect. So, see you tomorrow. Remember, don't be afraid of chemistry. Chemistry is very simple. So chemistry should not make you to be afraid. People in biological sciences, that some people in marine, they don't like chemistry. Another thing I want you to know, I want you to like chemistry. When you smile at things, things smile back to you. So like number one thing for you to pass this 213 to have it A, remember our goal is A. You must like chemistry. Even if you don't want to like it, just say, because I want to pass it, I like chemistry. Please, the essence of me doing this is to discourage you from going for tutorial. There's nothing you need tutorial for as long as 213 is concerned. If you are in my class, I told you guys that as long as 213 is concerned, I must make sure you pass it. But don't go for tutorial. No, you don't need outside tutorial. Don't go and spend that money. And I told you that if you have excess money, please, I'll share my account number. Send that money to me. Please, I don't want you to go for tutorial. I want you to stay with me online, ask questions on the platform that we are in. The problem I don't want to open that platform is that if I open that platform, people are going to bombard it and people might not even understand. So whenever you have any question, please chat me. I'm going to share that question and answer it on the general group. But tomorrow, for the sake of the test tomorrow, I want everyone to be available so that we can do the general revision for the 3 topics. But if you know you have not subscribed to this channel, you have to subscribe and share with your loved ones. Together, your A is sure. So, bye for now. Bye, everyone. I will send the past questions. Sorry about that. At times I can be very, very busy. So I will send the past question. But maybe tomorrow I'm going to see if we can deal on some of the past questions. But if we finish what I want to talk about tomorrow, you will not have any issue on 213 class text. And I want us to be making this broadcast maybe every week, in the sense that so that all the new topics are being treated, we can also come and revise them here. The essence is that so that before exam, you will not have fear. I don't want you to have fear. That's the sense of this. I don't want you to entertain fear of any kind. Okay? So don't be afraid. 213 is a walk over course for you. You're going to have A. And anybody that failed 213 is people that are going to have B. I don't want to be happy with those people that want to have B, but I'll pity them. But my best fans, my lovelies are people that are having A. So let's aim at A, right? Bye. Tomorrow.